So at the end of the last video, we derived this equation 5.88, that was the defining an ordinary differential equation which we can solve for sigma r. All right. So this is a non-homogeneous ordinary differential equation. Um, in the case where we have our cylinder is not rotating, so basically if omega is equal to 0, the right-hand side of this equation will become 0, and we'll be left with this differential equation here. Okay, so this is a second order differential equation. All right, we can assume an equation sigma r is equal to c r n, where n and c are constants, and we can plug in that equation into here to obtain the following solution for sigma r. Okay, so if you plug equation 10 into equation 6 on the last page here, all right, we can then all right, so we plug in equation 10 into equation 6, we'll get this equation here for the stress in the theta direction. Okay, so we now have two equations for sigma r and sigma theta. The only thing now is we need to determine our unknown constants, C1 and C2. Alright, so we can use the following boundary conditions. So we know that the radial stress should be equal for a thick walled cylinder, should be equal to the internal pressure at the internal radius, and that the radial stress should be equal to the external pressure at the outer radius. So if we plug in those two boundary conditions into equation 10, right, we will obtain the following values for C1 and C2. Okay, we can then plug in C1 and C2 into our two equations, equation 10 and equation 11. So these two equations, so we're just going to plug in C1 and C2 into our equations for sigma r and sigma theta. And if we do that, we'll end up with these two equations for the radial stress and the tangential stress. All right, so we'll get equation 12 and for the radial stress, and equation 13 for the tangential stress. Okay, so there are going to be some special cases for thick-walled cylinders that we might consider. So one case would be for the case of a completely solid cylinder. So in the case if you have a completely solid cylinder, all right, there can only be an external pressure all right, so our radial stress would be equal to minus our external pressure, and our tangential stress would also be equal to that. Okay. The second case is that if you have the length of your cylinder is not negligible, meaning that you do have a stress in the z direction, and the cylinder has closed ends, so sigma z is would be totally constant along the length in that case. Then you'd use this following equation here to determine what sigma z would be equal to. Okay. In the cases of a thick-walled cylinder, since there's no shear stress in our system, our normal stresses, sigma z, sigma r, and sigma theta, are your principal stresses. Okay, so and you can use those three normal stresses as your principal stresses to design thick-walled cylinders. Okay, and you can use the appropriate failure criteria for the material that you're using. So for ductile materials, you'd use von Mises, Tresca criteria, and then for brittle materials, you might use the maximum principal stress or the Coulomb-Moore theory to design your pressure vessels. Okay. All right. So that concludes the derivations for the radial stress, and the tangential stress, and the stress along the z-axis for thick-walled cylinders undergoing internal or external pressure.